All right. So last time we went through all this stuff about uh, what are the conditions where it's reasonable to expect air resistance to be negligible. What are the conditions where air resistance is going to have a big effect on something's motion? Um, so if um, an object can be treated as in free fall, and free fall and projectile motion mean the same thing. Uh, so what does that mean? Um, when can you treat an object as if it's in free fall? That means it's not touching any other objects. And the effect of air resistance is small. Then um, the object accelerates downwards at 9.81 meters per second squared. So it accelerates down with an acceleration of lowercase g, which is 9.81 meters per second squared. Okay, so in free fall problems, you start already knowing the acceleration. If you're holding something, yes, that's touching it. So it's not in free fall until you let go of it, and then it is in free fall. What? Then you can think of it as one object. Yep. Oh, I see. So you're falling with holding a bowling ball, and you're falling, but you're worried about the bowling ball because it's expensive or something. Yeah, just throw the whole thing then, and it's all one object in free fall. Right. You and the bowling ball are one thing, and you're both screwed, depending on how far the fall is, I guess. Okay, so let's do an example. Okay, so let's say you're walking over the Franklin Bridge, and well, no, not the Franklin Bridge because I don't know how tall that is. Okay, so but you're walking over a bridge, and you want to know how high it is, but you don't have a tape measure that long, and so this is the bridge, and what you do, you have a stopwatch with you, and you reach your hand out over the. That's you. Here's the top of your head. Um, a shirt. It's not a shirt. Who's ever seen a shirt that looks like that? Okay, so you want to see how high this bridge is. So you reach your arm over the side and you drop this rock and you turn on the stopwatch when you drop it, and then you turn it off, hit stop when it hits the water. And we're going to use that to estimate how high this bridge is. So how high is this bridge? Um, all we know is that it takes 1.2 seconds for the rock to hit the water after it's dropped. Okay, well, this is a constant acceleration problem. We're still going to use those constant acceleration equations. Now we just happen to know what the acceleration is. But we're going to follow all the same steps. By the way, like this works, but you need to be really careful. There's no boats. Okay, just so the first step is we have to choose time equals 0, time final, position equals 0, and positive direction. Okay, so what do you want to choose is T0, the first instant where we want information or no information. It's stopped. And what about time final? What? Yep, water. Okay, and now position equals 0 in positive direction. These free fall problems, I think it's a good idea to just always sort of treat these things the same way. It makes it less likely you're going to make a dumb mistake sometime. And so what I usually do is whatever is like the lowest height, the lowest point that has an influence on the problem, I call that 0, and I choose my positive direction up. I'm going to choose 0 there and positive that way. So P equals 0 is at the water. Positive direction is up. And now let's start listing out what we know and what we want. The variables are the same as they were before: time final, acceleration, P initial, P final, V initial, and V final. So do we know time final? Do we know the time in seconds corresponding to the instant that we're calling time final? Yes, we do. That's given, so this is equal to 1.2 seconds. Do we know the acceleration? Yep, it's free fall, and so that's going to be 9.81 meters per second squared down. Up is positive, so down is negative. So that means that the acceleration is negative 9.81 meters per second squared. And if you always choose your positive direction up, that acceleration is always going to be negative. Do we know the initial position? We don't know that. That's the thing we want. So see if you can make sense out of that. When time is equal to 0, the ball is released from the top of the ring. And what we want to know is how high is the ball at the instant it's released. Okay, because we've chosen this as our 0. Do we know the final position? 0, yep. Do we know the initial velocity? The velocity at the instant it's dropped? We do know that. So whenever an object is dropped, at the instant you let go of it, it has the same velocity as whatever it's dropped from. So if you drop something from a bridge, a good quality bridge, the velocity is 0 at the instant it's released. You let go of it, and it's just sitting there, and then gravity starts to make it move. if you hold something out of the window of a car and let go of it, for that first split second when you let go of it, the velocity is 55 miles per hour in the direction the car is traveling. And then gravity starts to pull it down. Okay, I'll say that. I'll put that in your notes in a minute. There are a couple things that's one of a couple things that will be useful in problems. But yeah, so the initial velocity is 0 because it's dropped from something that's not moving. Do we know the final velocity? No, we don't. And this can be, people get caught up on this pretty often. So if you think of the path of the ball that we're looking at as being the rock, as being from when it's let go to when it hits the water, a lot of people think, well, yeah, the water stops it, and so its final velocity is 0. But at the instant the water touches it, it's not in free fall anymore. So we can't analyze it, including it hitting the water. All the only stuff we can analyze is from the instant after it's let go to the instant right before it hits the water. And at that instant, right before it hits the water, it has some high downward velocity that we don't know. Okay, so yeah, we don't know V final. Hopefully we can solve this problem without it. Okay, so of the 3 constant acceleration equations, let me write them again. We're not asked for it, so if we can find the initial position without it, we're happy. So I'm just going to leave it out of everything. So here are the 3 equations. V final is equal to V initial plus A TF. The second one says PF is equal to PI plus VITF plus 1/2 A TF squared. And the last one says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. So are there any of these 3 equations that have PI and everything else in the equation is known? The second one, yep. So PF is 0, and that's equal to PI, which we're trying to find, plus V initial times time final. So that's 0 times 1.2 seconds, plus 1/2 times the acceleration, negative 9.81 meters per second squared, times time final squared, 1.2 seconds squared. So we have that 0 is equal to PI minus, can someone multiply that for me? It's 4.905 times 1.44. .0632 meters. Good job with the just random significant figures. You know, I like that in this class because it makes the chemistry people so frustrated. And so now move this over to the other side, and you have that 7.0632 meters is equal to the initial position. So the bridge is just over 7 meters high. Then I moved it to the other side. So I added 7.0632 to both sides. Well, just from this point, I just added 7.06 to both sides. And so this is positive. Any other questions on that one? So 20 in the low 20s feet. Um, so before we get into more of these example problems, let me give you two things that'll be really useful. Um, so two facts that will be useful in free fall problems. First one is the one that that came up in this problem. Um, when an object is dropped, um, instant it's released, it has the same velocity as what it's dropped from. It's different if it says something is launched or thrown. Then, like if you launch or throw something from a moving vehicle, it's going to have, at the instant it gets launched, released, it's going to have a different velocity than the vehicle. But if it's just dropped, if all you're doing is just letting go of it, then its initial velocity at that instant it's released will be whatever it's dropped from. Yep. And even if, now this is a little hard to imagine, but think of like a tissue paper, a feather or something, and you're going 80 miles per hour in your car, a balloon, okay? And you let go of it. At the instant you let go of it, that balloon's going forward at 80 miles an hour. Well, yeah, but it just slows down really, really fast, okay? But yes, whatever you let go of has that velocity of what you let go of it from. Yep. You throw it straight down. Well, then you're going to have to calculate how quickly it was thrown, or it's given. Um, and really, you can think the way that it's the same is if you think of uh, it being on a vehicle, it's your arm, and you're letting go of it at the end of your arm moving. Then it's released with the same velocity that your hand has at the instant you let go of it. Yep. Yeah. Yeah. So we can't do it yet in one-dimensional motion, but we'll be able to do it in two-dimensional motion. Yep. Uh, so, like for example, bridge, building, car, elevator, whatever. These are things that'll come up in problems. And when you let go of the thing, at that instant, its velocity is whatever the thing's velocity was, the vehicle's velocity was. The second fact that's going to come in handy is if an object starts out moving up, it reaches its highest point and the velocity is equal to 0. So in any problems where it asks like how high something is at its highest point or whatever, the way you're going to find that is by setting its velocity equal to 0 and then um, solving for related variables. So let's do one like that. Okay, so a ball is thrown straight up into the air. Height of 3 meters. At the instant it's thrown, its speed is 10 meters per second. And we want to know two things. First, we want to know what's the ball's maximum height. So how high above the ground is it at its highest point? Um, Second, uh, let's say what's the ball's velocity? So it's going to be launched up from 3 meters in the air. It's going to get to its highest point. It's going to come back down, and on its way back down to the ground, it's going to pass that height that it started at. Okay, so what's the ball's velocity? It returns to a height of 3 meters. And then third, let's calculate what's the ball's velocity before it hits the ground. Okay, so the first one we want to solve is just we want to figure out how high the ball goes. So first, for part A, we need to make those 4 choices. What's going to be our time equals 0? What's going to be our time final? Our position equals 0, and our positive direction. What do you want to choose as time equals 0? Yep. So the instant the ball's released. And what do you want to choose for time final? Well, so this is the first one that we've done where parts A, B, and C, we're going to have to make different choices for time final. So, yeah, so we want to choose for time final when the ball is at its highest point. If we don't choose that for time final, we don't have any way of calculating anything at that instant. Okay. And then P equals 0. I'm going to just keep doing this the way I always do it. So I'm going to make that the ground. And the positive direction I'm going to make up. Yep. And we should probably do a problem eventually where we make different choices of all these things and see how it all works, yeah, you'll get the same thing. So now we have to choose out of our variables: time final, acceleration, P initial, P final, V initial, and V final. We have to figure out what we know and what we want. Do we know time final? Nope. Do we know acceleration? Yep. That's negative 9.81 meters per second squared. We know initial position? Yeah. So anything in free fall at any time during its motion, its acceleration is down at 9.81. When it's going up, that's its acceleration. When it's going down, that's its acceleration. At the instant it has no velocity, that's its acceleration. And let me help you sort of make sense out of that, okay? So if you throw an object up into the air, like in this problem, on its way up, what direction is its velocity? Up, right? And if you call that positive, it's positive. But its velocity is up. Is it speeding up or slowing down? Slowing down, right? It's eventually going to come to a stop and come back down. So if it's slowing down and its velocity is up, what direction does its acceleration have to be? Right. And on the way down, what direction is its velocity? Down. Is it speeding up or slowing down? Speeding up on the way down. So what direction does its acceleration have to be? Yep, down. So no matter what direction something's going, gravity is always making it accelerate down. Okay, do we know initial position? So that's the position of the object when time is equal to 0. What's that? And is it positive or negative 3 meters? Yep, because 0 is the ground, positive is up, so anything above the ground is positive. So P sub I is equal to 3 meters. What about P final? Do we know that? No? Do we want it? Yeah, that's the thing we're trying to find. What about the initial velocity? We know that. So it has a magnitude of 10 meters per second. Is it positive or negative? It's positive because it's thrown up, and we said up means positive. Okay, so this is positive 10 meters per second. And the last one, do we know the final velocity? Yes, this is the key thing for any problem that asks about the highest point, right? Final velocity is 0. At the highest point, it's slowed down all the way until it's stopped, and it's just about to start moving in the other direction. So it's at that one instant where it's not moving. Okay, is there one of these equations that works with these? I think the one that works is 2a times the quantity pf minus pi is equal to vf squared minus v initial squared. And so 2 times negative 9.81 meters per second squared times the quantity pf minus 3 meters is equal to 0 squared minus 10 meters per second squared. And if we multiply the 2 and the negative 9.81 through, distribute that through these parentheses, we have negative 19.62 meters per second squared times PF. And then we have two negatives, so that's going to be positive. 19.62 meters per second squared times 3 meters is 58 point, I always forget these at the beginning of the semester, 58.86. Can someone multiply that out? 2 times 9.81 times 3. Yes! And the units are meters squared per second squared. And that's equal to, so you're going to square everything in the parentheses. So that's 100 meters squared per second squared. And now you can subtract 58.86 meters squared per second squared from both sides. And you get negative 19.62 meters per second squared times P final is equal to 41.14 meters per second squared. Meters squared per second squared. Yep. And thank you. That changes everything here. Because this is positive, so now we have negative 158.86 meters squared per second squared. And now divide both sides by negative 19.62 meters per second squared. You can cancel the units first, makes it a little easier to deal with. 1 meter cancels 1 meter. Second squared cancels second squared. So the position final is equal to, it's going to be a positive number. What's 158.86 divided by 19.62? What? 8.08. I'm not going to round. Not this time. Next time I will. I'll round double next time just to make up for it. Okay, so the highest point is 8.08 meters above the ground. That's cool, right? I'm going to leave it wrong. Okay. Just because of the chemistry teachers. Any questions about that? Yeah, I know. You too. Yeah, I would guess. I would imagine that. Okay, so now part B. So now we want to figure out the velocity of the object, and on its way back down, it returns to the height of 3 meters. Okay, it goes past 3 meters on its way back down to the ground. So we still have to deal with these. In every problem up until now, we've been able to keep these the same for all the different parts of the problem. What about this time? Well, we can still keep time equals 0 the same. That's still somewhere where we know a lot of stuff. But we're going to have to change time final. So now time final has to be the instant where the ball passes 3 meters on the way down. Returns to the height of 3 meters. And these two things, I always keep these the same. So let's say 0 position is still going to be the ground, and the positive direction is still going to be up. And let's list out what we know and what we want. So any of the stuff at time equals 0 that we knew before, we know now. Yep. Yeah. Mm-hmm. Yep, you could. And you could also use the highest point. The instant it reaches the highest point, you could use that as your time equals 0 now too. Yep. I usually, if I can keep stuff the same, I keep it the same, because then you don't have to like look around for variable values. You know, you kind of have them already there. For example, now, since we're using the same time equals 0, anything that we knew before that happened at time equals 0, we can just copy over from before. We knew the position, we knew the velocity, and that those are still true. Yeah. Okay, so do we know time final? Do we know how long it takes to go from when it's thrown to no? Do we know the acceleration? Yep, that's always negative 9.81. Do we know the position at time equals 0? Yep, that's positive 3 meters. Do we know the final position? Yes, what is it? Positive 3 meters again. Yep, that's right. Um, do we know the initial velocity? Yeah, that's the same as it was before, 10 meters per second. And we don't know the final velocity. That's what we're trying to find. Okay, so is there one of those 3 constant acceleration equations that works with this information? What? The first one doesn't work because we don't know time final. Otherwise, it would. The second one doesn't work because we don't know time final. The third one, yeah. So we have to use the same one again. So we have 2 times negative 9.81 meters per second squared times the quantity 3 meters minus 3 meters is equal to v final squared minus 10 meters per second squared. This second term, the second factor in parentheses goes away. And so all of this is equal to 0. And so what we get is, 0 is equal to VF squared minus 100 meters squared per second squared. And you can rearrange that to say VF squared is equal to 100 meters squared per second squared. That's 10 meters per second squared. Yeah, squared VI. Yeah, sort of flip stuff. There's like 2 steps in there. Okay, so now VF is equal to, leave a little space here for no reason, 10 meters per second. There's something important that I missed. So, right, when you take that square root, it's plus or minus, and now we're going to use the physical meaning of these to tell us which one we want, the positive or the negative. So what's happening is it's saying when the thing is at 3 meters high, it either has a positive velocity of 10 meters per second or a negative velocity of, negative 10 meters per second. And that has to do with the fact that this object passes the point 3 meters 2 different times. It passes it once on the way up, right when it starts, and it passes it once on the way down. Which one do we want when it goes past that height on the way up or on the way down? On the way down, down is negative, so we want that one. Yes. So yeah, I was just going to talk about that. So you see, so look at the form of the question. So yeah, I asked this question because it brings up a really interesting thing. Um, so this didn't. So this all went to zero, and this going to zero was the reason that these have the same magnitude. And this didn't go to zero because these were both 3 meters. It just went to zero because they're the same. Okay. It doesn't have to be 3 meters. I mean, it could be 2 meters or 1,000 meters or zero or whatever. If these two heights are the same, the two velocities have to have the same magnitude. And so that means anything that you launch up into the air, when it gets back to that same height, if you ignore air resistance, which can be a big thing to ignore, has the same speed that it was shot with, which is, I mean, when you shoot a bullet, it's going so fast that even though it's really aerodynamic, there's a lot of air resistance. But if you ignore air resistance, that's why they say, like, don't, like on New Year's Eve, like, pew, 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 don't celebrate shooting bullets into the air, because when you neglect the air resistance, it returns to that height with exactly the same speed that it was shot with. Yep.
Could you find the time where it's at the peak, the highest point, by taking it the full time of it and dividing it by 2?
Yes, everything's symmetrical like that. That's right. But what you have to be careful of is, so at least in the problems I make, I usually don't make it, I don't ask you about the ending at the same height as at the beginning, so you can't do it that way to make you go through the steps, kind of, Yep. Yeah. Hmm. Right. Okay, so now part C, we want to figure out the velocity the instant before it hits the ground. Um, so do you think that's going to be, it's going to be negative because it's still going to be going down. And is it going to be faster or slower than 10 meters per second? A little faster because it's still going to fall 3 more meters being accelerated downwards by gravity. So let's calculate that one. So we can still use the same time equals 0. Time final now is going to have to be the instant it hits the ground. Position equals 0. I'm still going to, well, I'm going to just keep these the same. So we don't know time final. We know the acceleration. We know the initial position is positive 3 meters. We know the final position. What's the final position? 0, yep. We know the initial velocity is positive 10 meters per second. And we want the final velocity. This one's going to use that same equation again. 2a times the quantity P final minus P initial. And that's equal to V final squared minus V initial squared. So we have 2 times negative 9.81 meters per second squared times the quantity 0 minus 3 meters is equal to V final squared minus 10 meters per second squared. So we have 2 times negative 9.81 times negative 3. That's 58.86 again. And the units are meters squared per second squared. And that's equal to V final squared minus 100 meters squared per second squared. And so V final squared is equal to 158. We've already seen this number today. It's so predictable. 158 meters squared per second squared. And so what's the square root of that? Okay, so V final is equal to plus or minus 12.6 meters per second. It's on the way down, which is negative, so we want that one. So in that last 3 meters, it picked up 2.6 meters per second in speed. Yeah. Yeah, I mean, all of these, yeah. Yes. Mm-hmm. Yeah. Uh-huh. Right. Yes. And, you know, um, you can think of this as like the position. Don't write this down. I'm just going to write this and then I'm going to erase it. But if you think of the position as a function of time, what you have is the initial position plus V initial times T plus 1/2 A T squared. So if you plot position versus time, any one of these motions is a concave down parabola. Well, no, it's only concave, depending on A. For the free fall, A is negative. So it's a concave down parabola. And so any symmetry things that happen with that parabola, you can come up with problems that show that. That's sort of what you're picturing, I think. Yep. The way you derive those equations is you start with acceleration as a function of time being equal to a constant, and then you integrate. Right. Yeah, you can derive those. Yep. And those, the first two equations you can mix up to derive the third one without calculus. But the first two come from integrating this constant. Okay. Um, quiz time? You need this long for the quiz? That's what I thought. Okay, let's do one. I'm going to give you one, and you see if you can make some progress on it, and then I'll go through it after I give you some time. Give you a chance to sort of see what things you're getting hung up on and stuff, and then we'll do the quiz after that. Okay, so this time, let's say that so you have this big hole and a ball launcher on the end of the pole. I don't know why. And you launch a ball down towards the ground from a height of 10 meters. And it takes 0.7 seconds for the ball to hit ground after being launched. What's the ball's starting velocity? Okay, so it starts out with a velocity going down. It starts out with a height of 10 meters. See if you can figure out what that starting velocity is based on this information. Try to go through all those steps for now. I mean, later, as you've done a lot of these problems, you might start cutting out some of the steps and just doing them in your head. For now, I would recommend just going through all of them explicitly. Okay, so time equals 0 is going to be the instant it's launched. Time final is when it hits the ground. Yeah, but I'm making these 4 choices about how to orient everything. Position equals 0, I'm going to put on the ground. Positive direction up. And now what we know and what we want. Time final in this one is given. It's equal to 0.7. Acceleration we know is negative 9.81. Initial position is positive 10 meters. Final position is 0. We want the initial velocity, and we don't know or care about the final velocity. The equation that works for this one is PF is equal to PI plus VI TF plus 1/2 ATF squared. So we have 0 is equal to 10 meters plus 0.7 seconds times VI plus 1/2 times negative 9.81 meters per second squared times 0.7 seconds squared. So 0 is equal to 10 meters plus 0.7 seconds times VI. What do you get if you multiply all that together? Minus 2.403 meters. Because we don't know the final velocity. No, the it's before hitting the ground. Yeah, as soon as it hits the ground, these equations are invalid. You know, because it's not in free fall anymore. That is 1/2 times negative 9.81 times 0.49, and this shouldn't be squared yet. And so you get VI is equal to 7.597 negative divided by 0.7 meters per second. So can you divide that for me? Negative 10.85 meters per second. Does it make sense that it came out negative? Yeah, because it's launched in what was our negative direction.